All right, so start working through this problem. What do we have to do to figure out the pH of the solution?
Calculate the amount of, I forgot what. The amount of something, it's like.
The amount of something. Basically, these neutralization reactions are pretty much always going to be excess reactant problems. We need to know the concentration of what's left over. Because if it's a strong acid and a strong base, then whatever's left over is either going to tell us our H3O plus concentration, or it's going to tell us our hydroxide concentration. And either way, once we know that, we can get to pH. Right, so start by writing out, you don't need the rest of the reaction in order to do this, but it's good practice for an acid-base reaction. Write out your products. Figure out how many moles you have, what's running out first, what's excess. And I'll give you a few minutes and I'll start working through it. Properly balanced. We're good on balancing. Then what's the next step on the stoichiometry problem? Put everything in moles. So 0.325 grams of lithium hydroxide. Lithium's about 7, hydroxide's 17, so somewhere around 24. Yeah, real close. 6.9. So it might be 23.9. Zero 1 5 ish. If you haven't pulled a calculator out yet, basically all we're doing today is practice with pH in these calculations. So you're going to want a calculator.
0.0098, so that just be 0.01.
98. We want even more than one more than that because we have 3 sig figs here, right?
98.
9.009. 136 sounds more reasonable.
Oh, you did the.
We all got the same answers. But there's one.
1 0.
Yeah.
One 136 or 135, either way works. This isn't quite 1.5 times bigger than this, so I had a feeling it was going to be close to point something 1.5. It shouldn't have been. If it was going to come out to be exact, something like 0.0098, then that should be something like 0.2.
Yeah, I just mixed up. I did 32.
There you go. That'll do it. the nitric acid. 125.0 milliliters. And for every 1 liter, we got to get to liters first, right? 10 to the 3 milliliters is 1 liter. 1 liter, 0.100 moles. Just as a quick aside, what's the pH of the nitric acid solution before the reaction? Concentration nitric acid is 0.1. What's your pH? What's log of 0.1? Anything that's an even power of 10 in terms of its concentration is going to give you a whole number for the pH. Because that's how logs work, right? So if starting concentration is 0.1 molar, then it's pH of 1. So 0.0125. All right, so these are excess reactant problems, but they're actually usually pretty straightforward because most of the acid-base reactions that we're going to see are going to be 1-to-1 stoichiometry, which makes it really easy to see what the limiting reactant is, right? We should all be feeling pretty comfortable with figuring out limiting reactant at this point. And if it's 1-to-1, how do we know what the limiting reactant is? It's the one that we have less of, which means the excess reactant is the lithium hydroxide. And it means we don't even really need to do any math to figure out how much lithium hydroxide is left over, right? Because every 1 mole of nitric acid is 1 mole of lithium hydroxide used, so we can just subtract it. All right, 0.0125 moles HNO3. Every 1 mole HNO3 used is 1 mole of lithium hydroxide used. So 1/1. So our excess lithium hydroxide is going to be what we start with minus what we use. All review so far, right? Well, technically this whole slide's review, but we did only have 1 day with pH, so I'm not counting the pH part. So that gets us through the first 3 parts of the question here. We want to know the pH after the reaction is complete. We need to know how much acid or how much hydroxide is left over. We need it as a concentration, right? Because if we're trying to get to pH, there's only 2 ways of getting to pH. pH's definition is the negative log base 10 of hydronium concentration or strong acid concentration. What's the other way we have of getting to pH? Close. We don't have any hydronium left, but we're still going to have a pH. We don't have any hydronium left within sig figs. Because we'll actually find out that our concentration of hydronium at the end is not 0, but it's going to be really close to 0 because we used up pretty much all of it in our reaction. So if all of our acid's getting used up, we don't just want our hydronium concentration because we don't have any hydronium concentration. But if we have leftover hydroxide, we can go around the back. Because we also know POH has a formula too. It's negative log base 10 of hydroxide concentration. And that we do know now, right? Well, we know how many moles are left. We still have to put it in concentration units. Right, so for these strong acid, strong base reactions, it's always going to be one of these two routes. Either you're going to have leftover acid, you find your concentration, you plug it in. If you have leftover base, you find your concentration of hydroxide and plug it in, and then you just have to do 14 minus to get pH.
Would there be a chance that we had pH and POH like excess?
If you have pH and, so you always have pH and POH because you never have zero of either of them. Sometimes it's just such a small amount that gets lost in the sig figs. Well, at the end of this, we'll calculate how much hydronium is still left based on the pH we calculate, but it's going to be like 10 to the minus 10 moles per liter. And a number that small is basically zero when we're talking about adding and subtracting, right? So if we have leftover hydroxide, our final concentration of hydroxide is going to be that 0.0011 moles over our total volume. What's our total volume going to be for this system? Just like that problem on the midterm, right? Our final volume is 125 milliliters. Right? We took 0.3 grams, so a pinch of salt, and we added it to 125 milliliters of the solution. So our final volume is 125 milliliters still. Or 0.125 liters. What do we get for our final hydroxide concentration then? 0088 or 088?
Yeah. 20.
Two zeros. Yeah, that seems about right. It's bigger than that, but it's not 10 times bigger. Addison? Because our standard, we want it in molarity. So which always has to be moles over liters. That's just our standard. And remember that these brackets, the square brackets, always mean concentration in moles per liter. All right. So then what's POH going to be? Something close to 2, right? Something just like 2.1 maybe.
5.
Right, so all I did was I took this 0.0088, took the log of it on calculator, and then it's going to come up as negative 2.05. And then because our POH has a negative sign in there, it cancels out. Right, so POH is going to be 2.05. And because this was, remember how I started out this talking about pH by reminding you that anytime you take a log of an even power of 10, you should get a whole number, right? This is pretty close to 0.01, right? So if it was 0.01, then we take a log of it, we would get -2 exactly. It's not exactly that, but it's close enough for doing mental math. Right, so as far as that reasonableness check goes. So if POH is 2.05, how do we get pH.
Fine. It's not fair.
Yeah, we just use this expression right here. So pH is gonna be 11.95. So to finish the thought about, well, how do you have a pH if there's no hydronium left? There still is some hydronium left. We talk about equilibrium on Friday. We'll start talking about some of these concepts in more details and how the math works out. But if we want to find out what the hydronium concentration is now, well, pH is equal to negative log of hydronium concentration. We know pH, right? So negative 11.95 equals log of hydronium. And you undo the log by doing 10 to the power of both sides, right? This is log base 10. So if we want to get rid of it, we do 10 to the power of each side. So 10 to the negative 11.95 is our concentration of hydronium. 1.1 times 10 to the minus 12 moles per liter. So really close to zero. It's not zero. It can never be zero. In water, you will always have some hydronium and some hydroxide. The more hydroxide you have, the less hydronium you have, but you can never get it to zero. And so you'll always have some amount of hydronium left. All right, so finding these pH for these limiting or these neutralization reactions is always going to go the same route. It's always figure out what you have left over. And if you have hydronium left over, if you have acid left over, you can just take the negative log of that concentration and you're done. If you have hydroxide left over, you take the negative log of it and that's your POH. And then you do 14 minus that. So it's one extra subtraction problem. The only way that this gets any more complicated for strong acids and strong bases is if it's not a 1-to-1 ratio. There are a few strong bases, like calcium hydroxide has 2 hydroxides to it. In which case you do have to do a quick stoichiometry step to get your excess reactant. If you go back and look at your midterm, I'm about 80% sure that that's the exact problem that I asked you on the midterm. Was a strong acid plus calcium hydroxide, what's the concentration of the excess reactant? The only thing we're adding at this point is taking the negative log of that concentration. Right, so if it feels like it's repetitive, like it's building the same way over and over again, it is. All right, any questions before I erase this? Olivia? Again, sorry, Gloria.
Does the I feel it's kind of
Mhm.
can you see, you get the pH for the in the answer, like, you think in your answer, would it be the pH or the?
pH. So because it's somewhat arbitrary, because POH and pH are both reasonable ways to talk about how acidic a solution is, but pH is just the standard. Acidic solutions are just way more common in nature in general, unless you get into geology. In living systems especially, acidic solutions are way more common. And so we decided as a group the scientists of the late 1800s decided we were going to rank solutions acidity in terms of hydronium concentration, not hydroxide. So all of these questions will always ask pH, even though it's kind of arbitrary. There's no reason why we use pH over POH. It's just convention.
But your answer is 1.1.
So no, this would be your answer for this one. Just box this, and it doesn't even have any units. So you have to write pH equals to give that number context. And because as you could write 11.95 pH units, but it's basically a made up unit. It's just a, because once you take the log of something, the units disappear.
I'll say for pH.
So for pH, always go to the hundredths place. Because logs and exponents have a third set of rules for sig figs, and I'm not going to make you learn those. So you just always go to the hundredths place when you take the log of the concentration. Doesn't matter how many sig figs you started with. Go to the hundredths place. Else?
All different.
So if we talk about strong acids and strong bases, what does strong mean in the chemistry sense? Completely reacts, goes 100%. Basically, we can do it like stoichiometry. If it's an equilibrium reaction, it doesn't go to completion. And so for weak acids, we actually have to find the pH a different way. So as long as it's a strong acid and a strong base, it's going to look like this. On Friday, we'll talk about weak acids in more detail, but basically we have to solve an algebra problem. Instead of just saying we use up all the reactant. And that's it. That's all we're going to do for this class. Is just those two cases. There's strong acids and strong bases. There's weak acids and weak bases. And that's as far as we'll take it. Yeah, man. It would be a good, so I think I don't remember what I've said in the past, but I believe when we get to the final exam, the closed book part of the final is going to have a strong acid, strong base neutralization. It's going to have this question basically, except just find the pH. And I believe usually you can tell based on the type of arrow that's drawn. So I have actually, I think I don't even have all 7 of them memorized. The 6 important strong acids were nitric, sulfuric, perchloric, HCl, yeah, hydrochloric, hydrobromic, and hydroiodic. I believe the last one was chloric. That's the one I'm 80% sure on. And that's not an exhaustive list. These are just the ones that are most common based on polyatomic ions. There's other really strong acids that are not based on polyatomic ions that you know. So, but in general, if you see this reaction written like that, it's a strong acid. If the reaction is written like it's written like that, that right there tells you it's not a strong acid. That type of reaction arrow is called an equilibrium arrow, and it tells you it's not going to go 100% to the products. And in this case, you need more information to be able to solve it. Which I suppose we could talk about that today, or would you rather do more practice of these? I've got about 3 more of these lined up.
Practice.
More practice. Then let's do it again. And in this case, I want you to give me fill out this entire table. You gotta do at least two of these anyway to get to pH. But I wanna know pH, hydronium concentration, pOH, and hydroxide concentration. And there's your calcium hydroxide. This one I think is actually the exact one on the midterm. The reason I asked you an excess reactant question on the midterm was to get you ready for this. We just walked through one of these problems. So I'm gonna have you all walk through it or work on in groups. I'll walk around. So I can give you some feedback on this. Let's get some practice on this. Yeah.
By adding 7.4 grams, I mean the like.
I'll go with 2.8.
Okay. Fine. Okay.
You know what? I think I made these numbers close enough that if you don't put one more sig fig here, when you do the subtraction, you might wind up with 0 if you round right. So let's add one more 0 to our moles there. Yeah,
Like slightly more hydroxide than the acid, so it's gonna be slightly more basic than.
so right now,
Yes.
so because the hydroxide is your limiting reactant,
Yeah.
you're actually gonna run out of hydroxide, so it'll be more acidic.
Oh, man.
Right, because we started with 0.02 moles of HI and we're using 0.0197 moles. It should be close to 7, because that's pretty close to 0. And if I did my math in my head right, I think we get this. We also have nice convenient numbers for getting molarity, right? 1 liter means our concentration's easy to figure out. I just took this and put it in scientific notation. So having it in scientific notation is actually a pretty good way to be able to estimate these logs in your head, right? Because this is if it was 1 times 10 to the minus 4, we took the log of it, it would just be -4, right? -4 exactly. It's 3 times 10 to the -4, so it's a little bit bigger. So it should be between 3 and 4. 3
5.
So pH equals negative log of 3 times 10 to the minus 4. We go from there. If this was just a what's the pH at the end question, we'd be done. If we're trying to actually go through the process of finding POH and hydroxide concentration, we just have a little bit more left to do. As long as I did my math, my subtraction right in my head. Right, so Once you have pH, POH is just 14 minus pH. So 14 minus 3.52 gives us 10.48. Now we're really almost home. 10 to the, to undo pH or POH, you 10 to the. So 10 to the negative 10.48 equals your hydroxide concentration. So it should be something times 10 to the minus 11th, Philip.
What's it, negative 10?
Because remember our definition of pH has the, and POH has that negative in it. So POH is defined as negative log base 10 of hydroxide concentration. So if we want to solve for hydroxide concentration, first thing we do is we move the negative sign over. And then we do 10 to the power of both sides. All right, so that one is as complicated as these can get. The last piece of the puzzle, the last possible way I could make it tricky is by making it a 2-to-1 ratio instead of a 1-to-1 ratio. And that really was not that big of a deal. We just had to remember to do that stoichiometry step, right? To show that it was 2-to-1 in order to get our moles used. All right, questions on this one? Anybody see a step they still are trying to figure out? Diego?
For the answer of the polarity of hydroxide, why is it only one sig big? Is it because you're getting the 10 to the?
You're doing 10 to that power. You do subtraction to get here, so you keep it to the 100th place.
Yeah.
And then, but then once we do the exponential, basically all the sig fig rules kind of, go away. Basically, what you should do is keep 2 sig figs. If you have 2 decimals here, you should keep 2 sig figs in your answer, but I'm not going to mark you down on that. So your final answer for hydroxide concentration is
I got like 3.3 times the negative 1.
Good. All right, Michaela. Once we get to the up until you get to the point where you find the pH, I want you to still following your rules. But once you take the negative log, it doesn't matter how many sig figs you had, just go to the 100th place every time. Like I said, there are rules for that, but I'm not going to grade you on those. Destiny?
This might be last question. We started with the oxygen H into the negative. Like, why do we work on that side as part of the question first for now, and then for this one we did?
So for this one, we had our excess reactant. Whatever our excess reactant is, will tell us which way we have to go.
Okay.
In this case, we had excess acid. So we can find the hydronium concentration right away. On the last one, we had excess hydroxide, so we had to find POH.
Gotcha. Okay.
Right, that's the real difference here. There's really only 2 ways it can go. Either you have extra acid and you go in this order, or you have extra hydroxide and you go hydroxide first. All right, anybody else? I have another one. We want to do another one?
Sure.
Okay, let's do another one. Yeah, Hannah. And so this number, when you plug this into this isn't scientific notation when you write it like this. So this, that would be like a 0.5 point out of 10, maybe. But technically the best way to write it in scientific notation, which would be this. Oh, sorry, I switched the order.
Yeah, I guess.
All right, this time I'm really gonna give you a couple minutes to work together, so talk to each other, I'll come around, so everybody can get some feedback.
You have to balance.
Do you? The answer is always, but in this case, it's already balanced, right? pH beforehand. Reminder, you already have concentration, a strong acid. You just take the negative log of it. There's your pH beforehand right away. Just because the problem said what's the pH before and then what's the pH after. This is your pH before. Anybody stuck? Anybody want me to come text what you've got so far?
You have meters of the malts.
This is how the mold, they're being into the 1:1 ratio, then you know, you have more of your excess. You subtract what gets you. Yeah.
Who do we get from moles of the hydroxide?
Sodium hydroxide is like 74 grams.
Sodium hydroxide is really close to 40.
Yeah.
Isabel? It should be something pretty close to an even power of 10, because I know the molecular weight of sodium hydroxide is really close to 40 on the nose.
40.
0.00988.
Yeah.
Bet you left off the hydrogen, Diego.
I did 29 point nine there instead of 22.9.
There you go.
I have.
It's easy to do. Lots of numbers, right? Testing.
Oh, I was planning if I did this right.
Let's put it up here. I'll check it. I want.
Yeah, let's make sure we actually did it right.
I trust you, but
Oh, wait.
that's the wrong one. So. We have a little bit left of the acid, good, 5.115, good. Assuming you plug everything in your calculator, right, that all looks right.
And then, because it's only acid, because H is in front of.
Right.
That's how you know.
Yeah. That's how we would name it as an acid too, right?
Yeah.
That's perchlorate, but it's not hydrogen to make it neutral, so it's perchlorate acid. Right, how we feel about these? Yeah.
So. Did I get some now?
Mhm. Mhm.
There's one.
Right.
It's like.
Yes, but I think you did. You plugged it in wrong, because this, it shouldn't be 1.1, it should be 0.01. Here for your moles of the acid. Those numbers are right. When you multiply them together, you should get 0.011, not 1.1. Good. So once you have your constant, that's acid, right? So if you want pH, you take the negative log of your acid. So if it's a strong acid, it's the same thing. So weak acids don't dissociate 100%, so your hydronium is not the same as your acid concentration.
These are in the market. I'm making like I'm making this go for.
Okay.
Right, how would you know if it's on? Or how would you know to use? Okay, so you.
If that's what you have left over. It's always going to be based on what's left over. If you have hydroxide left over, you can use pH.
Okay.
And then I asked you over here next. So the 1.02, where's the number? Get there? 2.1. It just happened that they're saying.
You know what I just did?
No, your final second.
I'll get for you. I think you can answer.
Yeah.
We did it long. For the first time, but. Oh, you did it.
It's not the law for leaders, and you don't have a role leader.
And then they go. What's your Excel?
This one is so draft, you're got to the and you can say, okay, if I did the same, I had 1,000. So we're at one.
You have way more than that, no, not way more, but you have more that.
This means more.
The hydroxide.
Give you your moles. And it should give you that, it should give you 0.011.
Do you think it?
Liters times polarity. Because then liters and cancel out, which is the conversion, right? Your head's the right one. How we feeling, everybody? These take a while, but we can call it the same thing, right?
I have a question.
Yeah.
You must have been so I have very advanced control. How do we go in here? Have like.
Is this the same problem we're working on now, or is it the last one? Okay. It's unlucky that you wound up with the same 141.
How do we know that? Is that what's?
It depends on what's left over. So if you have excess base, if this is what you have left over, then you're gonna find your hydroxide concentration and then find POH. If you have acid left over, like we do in this case, you find out how much acid is left over and then take the negative log of that concentration.
I don't anyways, I keep this because the comment is wrong. But I also have these, but.
Right. Yeah, that's totally fine. That would have been the reasonable way to write it. I just switched.
I use it.
Yeah. Yeah, that's fine. So point,
All of my.
I think you got these mixed up because that's the one that should be 0.0098. The hydroxide is 0.00988. Is the 9.88 for 10 to the minus 3 is moles. Okay, up here. There we go. There you switched from there. Good.
And then like, I have this here, responder ratio.
Okay. Oh, I see what you're doing. Okay. So do subtraction. Does it really come out to be the same number? Off by a factor of 10?
1.1.
Do it all, feels like you.
Oh, yeah, it does wind up being the same. Okay, then yeah. So that's your mold. That's your moles of acid left over. Your moles of A
Okay.
excess.
Okay, so that's your mold of excess. Is that, yes?
So when I do this, like, how do I keep like a C?
Okay, so now you need to turn that back into molarity.
It's hard.
Molarity
I,
is moles by liters.
your. So it's gonna be, your first answer was. Your biggest number was 0.0110. Your uncertainty was in the 10 to the minus 4 spot. So.
0.115, right?
Yeah, there was a 10 in there because we had 3 sigmas.
So maybe 360.
So no, because after you do subtraction, it'd just be the 2. So you were right. It does, if you do everything in scientific notation,
Yeah.
usually that's better, but if one thing makes it harder, it's subtraction and adding becomes the same.
Back to the original question.
Yeah.
I don't know. So how would we find it if it were
So the OH is what you have more of. If your OH is what you have left over, excess, then you would do the same thing, except you look
Then
at.
find the negative log
Right.
of your molarity.
So, oh, sorry, to finish, I see what you're saying, keep going from there. So then you go, if you know your final pH, then your POH is 14 minus 2.01. Right, because pH plus POH always equal 14.
I don't think I need 7. I've reached that page.
You haven't yet, so that's why you can't get to your hydroxide concentration until after you get pH.
Oh, wait, I don't know if I can figure this out. How would you know that if you're looking for H3O?
You look at what your excess is.
So they use my excess.
It's your acid, and that tells you you're looking for hydronia. You're looking for the how much excess is the concentration of the excess.
And
Oh, maybe 8.
Right.
It would just be.
Yeah, whatever the excess is, leave it off right, and find that concentration, and that's how you get pH or POH. I think. Go, we're almost done with class, right? So. It's one of those things, I think you've got something flipped in your head. And I, so if you go away from it and come back to it in a couple hours, you'll be like, I think you get. If you're asked if what left over, find the concentration is left. Right? Turning to the concentration.
Would that be on kind of this?
Not quite, that's still moles, not mole area. You got moles from me. And then. It would be, except we don't actually have, we only have,
Oh, you have to use that.
yeah,
Could be, 0.150.
over. That number, you can take the negative log of.